Welcome to the course on FPGA based signal processing systems. We'll continue with the infinite impulse response filter design. The Butterworth filter, which is the type of analog filter. We had seen in the previous lecture that how this analog filter can be discretized using the impulse invariant and the bilinear transform. So, designing this analog filter to get this HIFS, one way is that Butterworth filter or the Chebyshev filter, the types 2, 2 of 1 or 2. And there are other analog filters as well. So, in this course we will be focusing on 2 of this. We will design the Butterworth filter specifically with some of the specifications added to it, and Chebyshev also. So, whatever we had learned so far in the IIR with impulse invariance and then the bilinear transform and the Butterworth filter, the pole structure is in the S plane. That's important to know, and what would be the order of the filter. So, with this, if once we obtain the coefficients in the Z domain, that is, that we have the transfer function of the IIR filter with all the coefficients, or y of n, the difference equation of the IIR filter, then we'll go for the module IIR filter, clock, reset, data in and data out. So, data in to the structure of the IIR and what is the data out of this. So, x of n, what we have specified in our notations are the inputs, and data out y of n is the output. Clock and reset are. So, parameters we define this is 8th order, and the word size is input word size we can use at 8 bits here, and word size output will be, because we have this multiplication and addition, at least make this twice plus 2, so that the parameter size out will be done, and parameter b naught is equal to given 7 decimal, that is number 7. So, this we will be getting it from the design and scale it for the representation of 0 to 15 in that. So, parameters B1, B2, B3, B4, B5, B6, B7, B8 all are 0 here. So, we can have this parameters 0, okay, and then except this B0, okay. So, B1 to B8 are zeros, and then we have parameter A1, that is feedback coefficients. These are feedback coefficients. We have some signed or the decimal 46, not the signed one. 32 and 17, one is 0 and another one is 17, 32, 46, and this comes from the design. So, feedback, and this was feed forward. Feed forward coefficients. Once we have this coefficients, output size, define which one is output, data out is output from 0 to data size out minus 1, okay, that is 8. We had data size out we had given here is input with this 8, then 2 into 8 16 plus 2 18, at least we had 18 minus 1 would be this 0 to 17. So, 18 bits would be the data out, and input is again data size in minus 1, 8 minus 1 here 7, 0 to 7 input with this 8 bits, clock and reset are inputs. So, the declaration can be input and output can be first, and then you can define all the parameters as well. So, the order can be changed in that. So, these are reg. The reg is the samples input. Okay, what are the samples going to be? And that sample in is the variable we have declared, which is 2 dimensional. The one to order, this is the depth of the samples in on order 8. If you have this 1, 2, 3, 4 up to 8, data will be there of width 8 bits each. Similarly, samples out will have this also, the data size in minus 1. So, the data feed forward and feedback coefficients also given as the output here, data out output. So, data feed forward, okay. Then define this sample ones reg and sample out, feed forward and feedback. So, reg sample in and samples out, and the wire is this data feedback. Okay. So, from this we have the next, we go to the integer, define the variable which will be used in the for loop here. So, now coming to the data feed forward, actually. So, once we have this data feed forward, B naught that is the intermediate expression which we need to get assign data feed forward is from the design, that x of n. So we have this b naught and then delay this to b1. So delay it further, and similarly this coefficients we add them all. So we have how many adders record here. So this part, this is given as data feed forward here. So data feed forward equal to b naught into the data in, b1 into samples in. Samples in is getting, that is 1, which is shown over, which is stored where it will be a register stored in that, and b2 into sample 2, b3 into sample 3. It will have 8 such samples additions. So we get the intermediate feed forward network output. Assign that data feed forward is this. Okay. Next, assign data feedback. Once we have this, after this we have the adder, and y of n we have. So y of n is the output, and delay it may give the a1 and delay it again. This is a2. So this continues up to the 8th sample over here. Add everything. So data feedback. Okay, so here data feedback equal to a1 into sample 1, sample out, that is y of n, sample out, sample out 2, that is 1, this is 1 delayed and 2 delayed. Okay, so 3, 4, 5 and 6 and 7, 8, up to 8 samples we have this addition. So this addition is data feedback. So if you have once data out, and then all these things can be found. Data out is that samples out. So and we have to assign the samples out to data out, and what we have to assign the samples into x of n. So assign data out equal to, what is the data out? Y of n is data feed forward, that is this one, plus data feedback. So that is the case of we have the adding these two cases would give the data out y of n. So now having this always at passage of the clock, if we reset, then make this as k is varying from, depends on the order size, make all of them samples k equal to 0. Okay, in initial initialize this to 0, and output is also 0. If reset is 1, then all of them, this needs to be 0. This value samples in samples out should be 0 here. If not, that is else, what is the thing to be? Sample data in should be assigned to samples 1, that is input x of n is assigned to samples 1, and then so the samples 1 is multiplied with b naught, sample 2 is multiplied with b2, and so on. So data out should be assigned to sampled out. So that's what I was saying there, that in the previous slide, the data out is assigned to sampled out. And for once we have this first values 1 and 1 here, and then k equal to 2, from 2 onwards, that k in order up to 2, what should be the samples k. Sample k minus 1, that is the delay operation, k minus 1 assigning to samples in k to k. So this makes the D flip flop, that assigning everything to the according to k, and the same thing holds for k out also. We have this equal number of coefficients in the numerator and denominator. Though we have only one coefficient b naught, remaining b1, b2, b3 are 0. We made all of them both the polynomials in numerator and denominator equal, and the coefficients made them 0. So that's why we could use this k equal to order here. Okay, so samples out k and samples in out is equal to k minus 1. So end, and this is complete. Now the module is complete. So what we have to the order in which it is defined is here, the parameters. So declare all the parameters, that is what is the size and all those things, and the coefficients also. Once we have this coefficients defined, and then the input and output and the coefficients in parameters, we have used in some of the FAR example assign these coefficients. So instead of using assign, it's better way to have this parameter. Okay, and after defining the reg declarations, okay, so here we have the reg declarations, all of them, data out and data reg and wire. after this integer k, so have them computed, assign this with the, these are all outside the always block. Okay, so assign for this particular case, assign for the next case also, and then come add these two, you get this data out. So this data out, then we'll assign it to y of n and the data into x of n. This is for reset. Always at the passage of the clock we have these assignments which needs to be done, and then how to do the shifting using the for within the for loop. So with this code, we'll have the test bench for it. The test bench declare this and instantiate the, whatever we had these parameters. Need not declare the coefficients; it's already there. And the clock period, fix it. In this clock period, usually we do it with always hash 10 clock equal to not clock, or hash 5 for clock period of 10. So you can also define this in the clock period as a test bench and use it there. Then instantiate them after getting all the reg and wires declared in the test bench. Instantiate this module. Okay, then give the clock generation. This is the different way of clock, the clock period by 2 and clock equal to not clock. Okay, and then add the stimulus. What is the input we are going to give here? The integer, the initial begin here. Display can be given, display and monitor what is the data input and data output. Also reset is 1, so data in is 0, so there is no data given to the input to test it, and then apply this reset for some time. So that we have used the task operation, or here 2 star clock period, which also helps in the 20 for 20 time period, it is 1. After that it make it the reset 0. So this way, instead of writing the 100 200 calculating it, we can fix according to the clock period, we can make the reset 0 or 1. So taking the impulse response, data input is first the input 50 or 10 or whatever this input you can give, and for the clock period how much, 10 hash clock period, and then make this 0. So one clock period make this input data in and then 0. Okay. So observe the impulse response. After that we give the, for the particular clock period of I is varying from I equal to 20, step response. So how much time we are going to, so at least 20 clock periods we keep this we keep the step response. Okay, so that's how, that's why it is giving the 20 less than 20 here. Okay, so step response, for that reset make it 0 and 1 and then give the step value, that is 25, that would be resulting for the clock periods. So end and end module, finish this at a, so test bench which gives the impulse response and the step response for it, wherein your reset and the clock reset, how much time it should be made 1 and 0 with respect to the clock, it is given in this test bench. Whereas in the second part, which in impulse response, impulse input also, impulse input can be made for one clock cycle, need not be, it should be very short pulse for the impulse input and then stop. Similarly, step response can be made at particular and make it and stay there for a particular clock period of times. So that can be controlled over the clock period, or you can use the task as well. So the result which would the waveform editor gives this data input is 0 and it is given for the, at this point it is 50. So the data out, it for the 0 it is giving this, for 50 we can start observing it from here, the output for 320, and you can see this impulse input is stopped over here, and this is the response obtained from the data out. And over here this is 0, the reset is made 1 over here again. Okay, so you get the 0 for this clock edge. Okay, and then it becomes 0 next onwards, so it is giving the output over here, data out. So for the step response, this 25 here, it's made 25, the step response is given in this, taking the output and this data out. So in this case we have learned the code Verilog module. Once we have developed the code A naught and B naught, for knowing this coefficients, we can use it in the code. For A naught and B naught, compute the feed forward coefficient addition and the feedback coefficients additions, and then add them together to get y of n, and assign this input in the xn, also the output to y of n, data out sample and data in the registers here. And testing can be done in the test benches. The reset can be having with respect to the clock. We can make it for 1 clock or 2 clocks. It can be made 1 and 0. Similarly, the step response also, instead of forever to give, so for this many clock cycles, you can make this step response value be same. The impulse response can be here only one for one cycle. It is going to be given. After that, it is 0. So those can be controlled with task as well as the clock period, defining it in the way we did in the test bench. So instead of having the coefficients with the assign statement, we can use the parameter statement, very straightforward to reduce the reduce the logic. So that is a continuous assignment, which is not may not required in the assign statement, may not be required. So we have the parameters to use the parameters to declare the coefficients. So in the IIR case, impulse invariance and then bilinear transform and using the Butterworth filter design. So we can have the Verilog code done for this once we have the continuous analog filter, and from that two transforms, impulse and bilinear transform, can be used to discretize it and get the coefficients. From that coefficients, we can have the Verilog model. Use the scale coefficients here. We'll get to the because we have this bit size in the 0 to 15 or 16 bit width, we can use it. So these numbers needs to be taken into if you have ADC and DAC, it's not a problem that you can have them, these numbers converted into the real magnitude of the signal, input and output signals. So we will be doing the Chebyshev and the Butterworth again, some of the designs and how to get the coefficients using these two filters in the next few lectures for the IIR filter design. We'll also do more on the Verilog codes and how to directly write this instead of using the coefficients, and directly can we write that equation in the module. Okay, so if we have y of n equal to some coefficient x of n plus x of n minus 1, can we write that equation directly in the Verilog module? That we will see in the coming lectures. Thank you.